All right, so we are going to start the third section of Chapter 2, which is systems of linear inequalities. Um, and so this is going to involve, again, just like the previous section, two variables. And we are going to go ahead and have a couple different learning targets. The first being that you can graph and use just different varieties of inequalities to solve real-life problems. And then lastly, that you can graph and find solutions to systems of inequalities in two variables. Okay, we have like two terms or definitions here. Okay, the first is knowing that a system of linear inequalities in two variables consists of two or more linear inequalities in the same variables. So if your first equation has variables x and y, your second equation should have variables x and y. And that a solution of the linear inequalities in any ordered pair is a solution of each. So if I have an ordered pair 7, 8, it needs to be a solution to the first inequality as well as the second inequality. Okay, so let's actually just go ahead and figure out what solutions are. Okay, the thing that's really nice about these solutions is knowing that it's very, very consistent with all the other inequalities that we've done, as well as it's very consistent with the equations and such that we've done. If an ordered pair or a value makes it true, it's a solution. If it makes it false, it's not a solution. Okay, and that's really just how solutions work in general. Let's go ahead and see what that looks like. Okay, so if I want to check whether the ordered pair 4, 2 is a solution to the system of inequalities. Okay, let's just remember that we have ordered pairs x comma y, which is alphabetical order. Okay, and then I just have to plug them into each inequality. Okay, so I'm going to go ahead and plug it into the first one. So I'm looking at, well, x is 4, so I'm going to replace this x with 4, so 4, and then plus y, which is 2, and that needs to be greater than negative 2. Okay, and then as I simplify this, 4 and 2 together is 6. Okay, and I have 6 is greater than negative 2. Okay, so I'm looking at this, okay, whether this is true or not. Remember, with inequalities, the numbers do not have to be the same. The statement just has to be true. So 6 is greater than 2. This is a true statement. Okay, so what does that mean? That means 4, 2 is a solution to this inequality, which means graphically it's going to lie in this half plane, but it also needs to be true to this one. So yes, 4, 2 is a solution to the first inequality, but that does not guarantee that it's going to be a solution to the second one. So we have to go ahead and check the next one. Okay, the next one is x is 4, and then this one is minus instead of plus, so minus 2 is greater than or equal to 4. Okay, so then I get 4 minus 2 is 2. So I get 2 is greater than 4. Okay, greater than or equal to. So is 2 greater than or equal to 4? Well, hopefully at this point we can answer that and say that that is not true. That's a false statement. Okay, so since this is a false statement, okay, what that means is this solution is this ordered pair is a solution to this top inequality, but this ordered pair is not a solution to this bottom inequality. But for an ordered pair to be a solution, as we kind of mentioned in the definition above, it has to be true for this one and true for this one. In other words, it needs to be a solution to both inequalities. It is not a solution to both inequalities. It's only a solution to one. Therefore, this is not a solution. Now, if we wanted it to be a solution, it would need to be true for this one. It would need to be true for this one. Okay, great time to pause the video, try letter A on your own, and check it with your work here in a moment. All right, so I'm assuming that we've already checked this problem, or you've already done this problem and you're here to check it. So here I'm using the same ordered pair 4, 2, so I'm going to get 4 minus 3 times 2. Okay, and we're saying that that needs to be less than or equal to 4. So this is going to be 4 minus 6 is less than or equal to 4. 4 minus 6 is negative 2. Okay, and so then here I have negative 2 is less than or equal to 4. This is true. Okay, Now, do not jump the gun and assume that that means that this is a solution to each, because we have to check both inequalities. And then the next one, okay, x is greater than 1, so I got to replace x, so that is 4. And there's no y, so then that means that there's just no y for me to replace. I just have to only replace x. Okay, and that is greater than 1, which that is true. So as we can see here, it's a solution here to this inequality. It's a solution here to this inequality, meaning the system of them both combined, it is a solution. Okay. And again, this is very, very consistent with like all the other work that we've done involving solutions. It's just basically you have to do it twice with inequalities. Okay, let's move on to this bottom problem. Okay, now what we're going to do is we're going to graph the system, and then I want to talk about what it means to be a solution to the system in regards to our graph. So graphically what it's going to look like. As in the previous section and even our first chapter here, you're going to need to know how to graph straight lines. Okay, so I'm going to go ahead and get my straight edge out real quick because I know I'm going to need that. Okay, to be able to graph straight lines, you have to identify the form it's in. Okay, so we have two options. We have slope-intercept, and then as well as standard form. So I'm looking at this and I'm saying y is less than 2x minus 3. The y is isolated. It's by itself. That kind of informs me that it's in slope-intercept form. So I'm just going to go ahead and write this one down here. Y is less than 2x minus 3. Okay, and then I'll do this one here in black, and then we'll do the next one in red. Okay, so when I'm looking at this, I need to identify two things. I need to identify the m value, which is the slope, and the b value, which is the y-intercept. So this is kind of in the y is, I'm going to put equal to, but it's not always equal to, mx plus b. Because it can be less than, it can be greater than, it can be, less than or equal to, greater than or equal to. It can also be equals, okay? So what's my m value? So what's the value next to the x being multiplied by the x? That's 2. Okay, and so then for us, we often want to write that as a rise number over a run number. So rise over run here is 2 over 1. Okay, and then b is, well, it says plus b, but we have minus 3, so that would be like plus negative 3, however you want to look at that, and that's minus 3. So let's go ahead and graph that. So you always want to start here, okay, with the y-intercept. So you got to identify your x-axis and your y-axis, and that's going to be negative 3. So 1, 2, 3. Okay, so there's my starting point of this line. Okay, and so from here, I want to use my slope. My slope is 2 over 1. So that means for every x value I increase by 1, my y value is going to increase by 2. Okay, that's what this is going to be. So as I rise 2, my x value is going to go to the right one as well. For every x value I move to the right, my y value is going to increase by 2. Okay, so what does that tell me? That means I can go up 2, right 1. Okay, and that pattern, since this is a straight line, will continue forever. 1, 2, right 1. 1, 2, right 1. Okay, and you don't necessarily need every point, but just a handful to get yourself a pretty solid straight line. Okay, so that actually, speaking of solid straight line, this one may or may not be a solid line. Because we talked about in the very first section, and we've even discussed it in the last section, we have to identify whether these boundary lines, this line that I'm creating, is going to be part of the solution set, it's going to be included in the solution set, or it's going to be not part of the solution set, meaning it's excluded. So that means it's going to be part of it or not part of it. Okay, so when I look at less than, it doesn't say less than or equal to, because this line is going to be like the equal to part when this left side is exactly equal to this right side. But my inequality sign is just less than. It doesn't say it can be equal to. So we want the type of line where the line is not inclusive. Okay, so is that a dashed line or a bold line? Okay, hopefully we've identified now that this is indeed going to be a dashed line. Okay, dashed lines are going to be exclusive of the solution set, meaning that if I'm on this line, I am not part of the solution set. Okay, so in the last section, we discussed how linear inequalities split it into two half planes. So that means my solutions to this inequality are either going to be on this left side here or on this right side here. One or the other. It can never be both. So what I need to do is I need to identify where my solutions lie. So why don't you think back to the previous section and think about what did we do to figure that out. Hopefully in your minds you're saying test 0, 0, which is 100% correct. You want to test a point and see whether that's a solution or not. Because I can't have solutions some over here and some over there. They're either all here or they're all there. So what I do is I pick one point, any point on the graph that's not on the line, and you test and see if it's a solution. For us in my class, I'm going to suggest to you to test 0, 0, okay? I like to test 0, 0 because that is the easiest number to multiply. It's also the easiest number to add or subtract. So I'm going to go ahead and test 0, 0. Okay, and I want to see whether that's a solution or not. So I'm going to test whether it's a solution the same way in example 1 and example A above that we tested to see if it was a solution or not. So I'm replacing x and y with 0. Okay, well, 0 stays the same. 2 times 0 is 0. Okay, and then 0 is less than negative 3. Okay, so we want to think about this statement, identify this as a true statement or a false statement. So is 0 less than negative 3? Well, just think about the number line, okay, or a temperature. Is it colder? Because like the lower the temperature, the colder it is. So is 0 colder than negative 3? No, it's not, meaning that it's less. Like what's having more money, having $0 or owing somebody $3? Like you're in debt there, so you're kind of in the hole. Okay, so this is actually false. Okay, so what does that mean? That means this ordered pair with 0, 0 on it, this is not the solution side because we tested this point, and this point is not a solution, meaning that all of these points over here are not a solution. Because again, they're all over here, they're all over here. Now, in the previous section, what I would have you do is I would just say, hey, shade this right-hand side. Okay, but remember, we have a whole nother line that or half plane that we have to deal with. So that doesn't mean they're all over here, but that means I know my solutions are on this side somewhere. So instead of shading right away in this section, let's just draw arrows. We know that my solutions are on this side of that boundary line. We don't know the specifics yet, but we do know it's on the right side of that line. Which brings up the other line, okay? Because there's a whole nother line that we have to deal with here. Okay, and we'll have this one be the red one. Okay, and so this one is y is greater than or equal to the opposite of x minus 1. So as I'm looking at this, this is again in slope-intercept form. And I need to find my m value, which is negative 1, and my b value. It's negative 1. It's this negative 1 here, right? It's not this negative 1 over here if we look at our base form, but they do end up both being negative 1. Okay, so I can start graphing my line. Okay, I'm going to start at negative 1 here, and then I'm going to have a slope of negative 1, which is the same as negative 1 over positive 1, which is down 1, right 1. Okay, over and over and over and over again. Okay, so I just plot a few of them, not necessarily all of them, just enough to get myself started. Then we have to ask whether this is a bold or a dashed line. Okay, so when it says greater than or equal to, that means that it is or equal to, it means it can be equal to. So this red line, if you're on the line, you are part of the solution set. Okay, so this one is slightly different from the other one, and this is going to be a bold line, meaning if I'm on this red line, I'm part of the solution set for the red line. Okay, lastly, I need to test my red line. I need to figure out, are my solutions below the red line or above the red line? Okay, so we can go ahead and we can test 0, 0 again, because 0, 0 is not on the red line, so we can test it. Okay, and so then this one here, I'm going to have 0 is going to replace the y value, and then 0 is going to replace the x value as well. So here I get 0 is greater than or equal to. The opposite of 0 is 0 minus 1, and 0 minus 1 is negative 1. So here I have the statement 0 is greater than or equal to negative 1. Okay, so I got to ask whether this is true or false. Okay, this one is true. Okay, so that indicates to me I can go ahead and say the side with 0, 0 is the solution. Okay. So that means it's above this red line. Again, I don't want to shade that entire area because we need the spots where the black line solutions are true and the red lines solutions are true. Not one or the other, but both of them together combined are the solutions. So we kind of have 4 quadrants here. So let's go ahead and just think about each one of them. Let's think about this one here. So would my solutions lie in this little area in here? Okay. Hopefully you're saying no. Pretty clearly this is the one area that's definitively not part of the solutions. Why? Well, because I know that my solutions are to the right side of the black line, and this is the left side of the black line. Right there already it's out of the question. But furthermore, with the red line, we know our solutions are above the red line, and this is below the red line. Essentially, this has no solutions whatsoever to the black or the red line. Completely out of the question. Okay, let's think about this like triangular looking area up here. Okay, let's think about whether that would be a solution. Well, if you look at the red line, I know my solutions are going to be above the red line. Okay, and this is above the red line, so that's kind of a good start, right? We know it's a solution to the red line. Okay, but what about the black line? Okay, so we know my solutions need to lie to the right of the black line. So although this area has solutions to red line, okay, it's not solutions to both, because that's what a system is solutions to both inequalities. Okay, so this has only solutions to red line only. That's what this little area is. And I'm even going to write that over here. This is solutions to neither. There's no solutions over here. Okay, and then what about down here? Okay, if we look here, this is to the right of the black line, which is good, but it's not below the red. It's not above the red line. It's below the red line. So this area is the solutions to the black line only. But where is the area that is solutions to each? It's kind of where our arrows are pointing to mutually. So I have pointing this direction and this direction. Okay, as you can see here, this area there is solutions to each. So my solution set is any ordered pair inside of this highlighted region. Okay. Okay, so let's just pick some ordered pairs and just graphically identify them as a solution. Okay, so there's kind of our visual of where all of our solutions look like. So what if I pick this ordered pair right here? Okay, whatever it may be. Is that a solution to the system? Yes, it is. Okay, what about this ordered pair right here? Is this a solution to the system? Although it's in it's a solution to the red line. Since this black line is dashed, it's not inclusive, it's exclusive. Therefore, this is not a solution to the black line. What about this point right here? Well, it's a solution to the black line for sure. It's to the right of the black line, but it's not above the red line. It's on the red line. But again, this bolden red line indicates to me that points on that line are solutions to the red line. So this is indeed a solution to this system's area. So go ahead and give 2 solutions of your choice that are, you know, we can go ahead and say this ordered pair here and then this ordered pair right here. I'll let you guys go ahead and find that on your own. Okay. Pause the video now. If you need a little bit of time here, pause the video and move on to letter B. Try it on your own. Check it with me right now. Okay, so I'm assuming that you've already paused the video, tried this out. So let's go ahead and see how you did. Okay, I'm just going to call the first line the black line, I suppose. And we have x plus y is greater than 4. Okay, this is in standard form. Okay, so if you want to put this in slope-intercept form, that's fine. You're going to get the same answer regardless, but I'm going to go ahead and do this by finding the x-intercept. okay, which means that y is equal to 0. So that means I can just say y, or x is greater than 4. Right, if I replace y with 0, it's gone. X is greater than 4. So 1, 2, 3, 4. Okay, and then I have to find the y-intercept. Okay, and then here I'm going to have to get, well, then I know x is 0, so that means y is also greater than 4. Okay, and then this line here, when I connect my dots, here, I am going to have a dashed line because it's just less than, not less than or equal to. And lastly, I need to test 0, 0. Okay, so here I can replace x and y with 0. And then here I get 0 is greater than 4, which hopefully we know is false. That means my solutions are going to be above this black line somewhere, but not on the line, just above the line, not on it. Okay, next we can do this as the red line. Minus y is greater than or equal to 3. Okay, so let's go ahead and find the x-intercept. X-intercept means that y is equal to 0, so I don't even have to write the y. I can just say 2x is greater than or equal to 3. Divide by 2. X is greater than or equal to 3.5 or 1.5. Or not 3.5, 3/2 or 1.5. So got to find x value 1.5. So here's 1, here's 2. 1.5 would be right about in the middle. Okay, and then we have to do the y. Go find the y-intercept. Y-intercept means that x is equal to 0. Okay, so I don't have to write x at all. I just have to go y is greater than or equal to 3. Then the opposite of y, so I have to divide by -1. If you recall, dividing by a negative number makes me flip my sign, so y is less than or equal to -3. 2, 3. Okay. And then this one will have a bold line because it is greater than or equal to. Okay, and then I have to test 0, 0. Okay, so this means 0 and x is 0, y is 0. Okay, so I just took this equation and or inequality and I replaced x and y with 0. So I get 0 minus 0 is greater than or equal to 3, which means 0 is greater than or equal to 3. Again, is false. So if this is where 0, 0 is, this is where my solutions are to the right. Okay, so again, I'm looking for the overlapping area, the spot where it's solutions to black and red line. Okay, so that would be this little area here. All right. Okay, go ahead and give two solutions. I'm just going to give you a couple examples. For example, anything in that highlighted region, that would be a solution. This ordered pair right here would also be a solution because that line's bold. This ordered pair right here on the line would not be a solution because that line is dashed and it's exclusive. Okay. So now the next, what we're moving on is we're just going to make it, honestly, just a little bit more complicated here. What we're going to do is we're just going to graph a system with three inequalities, okay, and everything's the same. We're just going to reason through the problem, okay? So this one, we're going to have three different lines. Let's go ahead and start with the black one. Okay, so this is x is greater than or equal to 2. Okay, so now this one here, it doesn't really appear as though it's in standard form or that it is in slope intercept as either. This is kind of one of those special cases that you're going to have to get used to and know. Okay, so we're looking at x is greater than 2, greater than or equal to 2. So as I'm looking at here, I want to find x is 2. So that's like right about here. And I know my x values, specifically just my x values, are going to be greater than 2. So let's just think about this. This is x value 1. Is that greater than 2? It is not. What about here? Is this x value greater than 2? No, this x value is still 1. So I know that as I move up or down from this axis, like as long as I stay vertically with it, like this is all x values 2, and this is all x values 1. So that means it's going to kind of create a vertical line. It is going to be bold because it's greater than or equal to. And now I just have to figure out where my solutions lie. They're greater than that, so here's x is 3, 4, 5. So it's basically everything to the right of this vertical line. So I'm going to go ahead and draw myself some little arrows to the right, knowing that my solutions are there. Okay, so then let's do the red line. That one will be next. So this one is going to be y is greater than or equal to negative 2. Again, this isn't really in any form. It's not really in slope intercept form. It's not really in standard form. It's, again, just going to be a specific case, okay? So we kind of know that x value lines or vertical lines kind of tells you that y value lines are going to be horizontal, but let's figure out why. So I'm looking at y value negative 2, so that's like right here. So as I move up or down off of that line, my y value changes. But if I just stay horizontal, my y value is going to stay at negative 2, which is what this thing is asking for us to do. So here I'm going to go ahead and just create a horizontal line through negative 2. Okay, and so then I know my y values are greater than that. So greater than or equal to, so as I move up, my y values increase. As I move down off the red line, my y values decrease. So it's going to be up. So currently, if we were just doing 2, it would be this little quadrant here, the overlap of these. But we still have one more line to do, and this one will be in blue. Okay, so I have 3x plus 2y is less than or equal to 12. Okay, this one is in standard form. Okay, so let's go ahead and find the x-intercept. Okay, so my x-intercept means that the y value is 0, meaning that 3x is less than or equal to 12. Divide by 3 to find out that x is less than or equal to 4. So I'm going to find x is 4. X is 1, x is 2, x is 3, x is 4. Okay, and then we have to find the y-intercept, which means that x is 0. Oh, so that means that 2y is less than or equal to 12. Divided by 2. Y is less than or equal to 6. So we have to find y value 6, 0, 1, 2, 3, 4, 5, 6. And when I connect them, are they going to have a bold or a dashed line? They are going to have a bold line. Okay, so I still need to figure out what side of this shaded, or what side of this blue line I need to shade, so that either to the left or to the right. So to the left or to the right. Okay, but as I look, I know that this kind of rectangle I've created, that's where my solutions are going to be based on the black and the red line. So that means either this little triangle here or this outside area is going to be my solutions. Okay, so we still can just go ahead and test 0, 0, meaning that 3 times 0 plus 2 times 0 is less than or equal to 12. This is 0. This is 0. So I get 0 is less than or equal to 12. Okay, so that means that it is true. So that means we want to shade the side that is below the blue line. So now we just have to find the overlapping area. Okay, so what I'm looking for is the area above the red line, to the right of the black line, but yet below the blue line. So where is that area? Okay, it is this small little triangular region right in here. Okay, this is where my solutions lie. So any ordered pair in that solution, and since they're all bold lines, any point on that triangle created in the middle there would be a solution. Okay, so now's a good time. I mean, these problems are really the same. The big thing, though, that you're going to need to know is that an x equals, or x whatever line is going to be a vertical line. A y equal line will be a horizontal line, and then any other line that you're going to see beyond that has been taught previously. So hopefully we kind of already know that, and we can kind of start to figure that out. Okay, so let's move on to example C, which is for you all to try. And go ahead and try that on your own. When you're done with that, check it with me, and I'm going to go over that right now. Okay, so first one's going to be black. So x is greater than or equal to 0. Okay, so this is kind of a nice one because 0 is on this axis here. So actually the line's kind of already done for me. So that's pretty nice. We just have to figure out shade to the right, shade to the left. It's a bold line because it's greater than or equal to. So that means it's to the right of the y-axis because that's where my x values are 0. Okay, let's do the y value line. Okay, we know this is going to be a horizontal line. Okay, this horizontal line is going to go through 2. Okay, so this one is dashed, though, I believe, because it's just greater than. Okay, not like a weird angle. It's hard for me to see these lines. Okay, so this is dashed. Okay, and then I just have to identify whether it's above the dash line or below. So I'm looking for y values greater than 2. So let's think if this is where y values are 2, 3, 4, 5, above it would be greater. So, and then lastly, the blue line. Blue line is in, I would say, probably most people's favorite form, which is slope-intercept. So m value is 2. B value is 6. We can rewrite 2 as 2 over 1. And what's going to happen is we're going to start at the ordered pair 0, 6, or the y value of, or the y-intercept of 6. 1, 2, 3, 4, 5, 6. And we're going to go up. This tells me up 2, right 1. Up 2, right 1. Up 2, right 1. Down 2, left 1. Down 2, left 1. Okay, and we're just going to go ahead and do this a couple times. Bold or dash line. So as you think about that, whether it's going to be a bold line or a dashed line, this one is going to be dashed because it's strictly less than. It's not less than or equal to. Okay, so I'm just going to go ahead and put a dashed line through all of these dots all the way through. Okay, lastly, I just need to identify whether I need to shade above or below the blue line. Okay, so we have to test 0, 0, meaning that my y value is 0, my x value is 0. Okay, so I'm replacing y with 0 and x with 0. So this is 0 is less than 0 plus 6, which is 0 is less than 6. So 0 is less than 6. Well, that's true, right? That's true. So that means the side with 0, 0 on it, which is to the right of the blue line, is where we want to shade. So we have all these different little areas, right? We have the little triangle in the middle, and then a whole bunch of different areas outside of that. So let's think. So I want to the right of the black line, above the red line, but to the right of the blue line, or below the blue line, however you want to view. Okay, so what it is, it's this kind of area up here, but you got to be careful, right? Because I want to stay to the right of that black line here. So that means this little triangle in the middle is not going to be included. So make sure you're not including that. That would be incorrect. And then it's just kind of this little traced in region right in here. All right. All right. Let's go ahead, finish this up, and let's find ordered pairs that are solutions. Obviously, you can pick anything in that highlighted region, and that would be perfectly acceptable. Let's just go over some more slightly complicated ordered pairs that might be a little more difficult to identify as a solution or not. Okay, so like let's think about like an ordered pair on the red line right there. Would that be a solution? It would not, because the red line is exclusive. It's not part of the solution set. What about like this one right here? That would not be a solution set because that line is dashed. It's not included in the solutions. What about this one right here? Okay, we've identified that that line is bold. So this specific one would be part of the solution because, you know, it's above the red to the right of the blue and on that black line. That qualifies. What about like one down here on this the black line down here? Well, although it's on the black line, therefore it is a solution to the black line, it's not above the red line, even though it is to the right. This here is only a solution to the black and the blue line, but it's kind of forgetting about the red one. So there's a lot of different parts going on here. So just make sure you're paying attention and having nice, neat work here is really gonna give you a lot of benefits as you move through these problems. Okay, it looks like we just have one more problem, which is our word problem. So let's go ahead and work through this. The ones that you're going to see are going to be pretty similar here. So let's go ahead and start this. Okay, so let's go ahead and read this one. So to get the most benefit to your health while exercising, you should increase your heart rate so that it is within your target heart rate range. Your target heart rate range is from 50% to 75% of your maximum heart rate. Your maximum heart rate is 220 minus your age for people aged 20 to 70. Okay, so we want to start by writing and graphing a linear inequality that shows your target heart range from people from 20 to 70 as a function of their age. Okay, so that means if you think about somebody's target heart rate, their maximum heart rate, it's 220, and then you just take away however old they are. So that means that this problem completely depends upon how old somebody is. So that's going to be our first variable. It's going to be a person's age, where y is going to be that heart rate. And what we're going to do is we're going to graph where that heart rate is going to be. So there's two parts to this, right? So there's the 50% and the 75%. Okay, so the target heart rate. So let's do the 50% one. So let's go ahead. I'm just going to put a little 50% here. We know that this is the 50% one. Okay, we know that y, the heart rate that we're going to have, is going to end up having to be 50% or 0.50 times their maximum heart rate. Let's think about why that is. Okay, because it says here that your target heart rate is from 50% to 75% of your maximum heart rate. So what I'm doing right now is I am tagging that lower limit, the smallest limit, that 50%. So it has to be 50% of your target heart or your maximum heart rate. 50% of indicates multiplication, or if I just wanted to say if I wanted to find 50% of something, you would take 0.50, multiply it by what I'm looking for. So I'm going to take 0.50 and I'm going to multiply it by your maximum heart rate, which is 220 minus your age. Okay, so now what I need to do is I need to figure out what inequality sign it's going to be. So if we think about the problem, we have like an upper limit, which is the 75%, and a lower limit, which is 50%. And you need to get your heart rate in between that 50% and your 75%. You want to be somewhere in there just to get a good benefit from exercising. So if I'm talking about that lower limit and I want everything to be above it, what inequality sign would it be? Well, I think we can obviously exclude less than or less than or equal to, because we want it to be above. So we know it's going to be some brand of greater than. Now we just have to figure out if it's going to be greater than or equal to. So your target heart rate is from 50% to 75% of your maximum heart rate. Basically, from what I'm reading here, it's indicating to me that it could be 50%. It also could be 75%, like included 50% and including 75%. So I think it's fair to say that we can go greater than or equal to here. Okay, and so then let's go ahead and just simplify this. We haven't really seen anything like this that we've graphed before. So let's go ahead and distribute 0.50. So this is going to be y is greater than or equal to 0.50 times 220 is 110. And then this is going to be minus 0.50x. Okay, let's do the 75% one. It's very, very similar here, the 75% limit. Okay, this one, we know our target heart rate is going to be 75%, so 0.75 times your maximum heart rate. Your maximum heart rate, again, is 220 minus x. Okay, now I have to think about what kind of inequality sign am I going to have. If this is my 75% limit, I'm trying to get in between 50% and 75%. If my 75% is my higher, I'm trying to get it between 50 there. It makes sense that it's going to be less than. Or equal to, for the same reason that we talked about above. There doesn't really seem to be any reason to say that we can't be at 75% exactly. Okay, and so this is less than. Well, I'm not quite sure what 75% of 220 is, so I'm just going to use calculator. 0.75 times 220 is going to be 165. And then this is minus 0.75x. Okay, then what we want to do is, there's kind of a limit on ages also, right? Because this only works for somebody between what ages? Hopefully you're reading the problem, you're identifying that this really only works for people from age 20 to age 70. So if we're trying to target those people specifically, we need to talk about just the x values, right? Because x represents age. So I know that x has to be greater than or equal to 20 because the person can be 20, but the person also needs to be less than the age of 70 for what I'm trying to look at. Okay, so we kind of have a lot of equations here, so I'm just going to put bullet points by the ones we're going to deal with here. So we actually have 4 here. Okay, let's go ahead and do the x and y variables. Okay, so I know, well, let's go ahead and I'm just going to bold these lines here because it's bothering me that I don't have an axis here. All right. Okay, now it's important to know that our x and our y axis actually do not have to go by the same amount, and I think this would be a really good example where they're not going to, because one's talking about age, one's talking about heart rate. They're like so entirely different that they don't necessarily need to be scaled at the same amount. So I know I have to include 20 and 70 here, and I have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. I think it seems very reasonable to just go by tens here. That's going to include both of those. So 10, 20, 30, 40, 50, 60, 70, 80, 90, 100. Okay, and this is going to be a person's age. Okay, so let's go ahead and graph this one here. Okay, x equals line is going to be a vertical line through 20. It will be bold because it's greater than or equal to. Okay, so I'm going to put a bold line here, and then the exact same thing with 70. So what this is doing is this is just kind of putting boundaries on where my x value is going to be limited by, because we're really only interested in people between the ages of 70 and the ages of 20 and everything in between. Okay, so let's just put a little check mark there. We know we're done with those two. Okay, let's go ahead and do this one here. Okay, so this idea of slope that we've dealt with in the past, although it's very, very helpful, this is one where it's not going to be, because we don't really know what we're going to go by. We know that the graphs are decreasing because the slopes are negative, and one's going to start at 165 and the other one's going to start at 110. So let's go 110 minus 0.5 times. Okay, so what we really want to do is we want to try to encompass all of that. And we know it's decreasing, so I'm not really sure how low it's going to go. So it seems reasonable to start at 0, but to get to 165 up here, I mean, we're going to have to go by, you know, so if I go by 20s, that'll give me the 200 here because there's 10 slots. So let's just go ahead and go by 20. So there's 20, 40, 60, 80, 100, 120, 140, 160, 180, 200. And this is my heart rate. Okay, so as I look through this, let's just go ahead and graph this one first here. I'm actually going to do these in different colors so it's a little more visually obvious. So let's go ahead and do this one in red. Okay, so the thing that's nice is that we kind of have already one ordered pair. We know like 165 is going to be the y-intercept. So as I look at this, okay, I know that like 165, let's say it's right here, right? Because this is probably 170, and so halfway in between those, give or take, is going to be 165. There's my first point. So the thing, though, is I just can't use slope and go like down 1, right 2, down 1, right 2. Because the graphs, I mean, this is going by 10s and this is going by 20s. It's just not how it works. They're scaled differently. This concept of rise over run isn't going to be as useful to us. But what we can do is pick a random x value ordered pair and go ahead and plug that in, get my second dot, and just connect the lines. So let's go ahead and pick, oh, this is 0.75 here too. So let's go ahead and pick 100. So we're going to pick x is equal to 100, and we're going to find the y value that goes with it. Okay, I picked 100 just because I know that that's going to multiply well by these decimals. Okay, so here I have y is less than or equal to 165 minus 0.75 times 100. Okay, so I can just go ahead and put all this in my calculator. 165 minus 0.75 times 100, and that's 90. So now I have this ordered pair, x is 100, y is 90. Let's graph that. X is 100, y is 20, 40, 60, 80. There's 100, so 90 is reasonably exactly in between. Okay, and it's a bold line, so I can just connect my two dots. Okay, and so this is my 75% line. So this is my 75% line of the heart rates. So we know, based on our less than sign, we can test this the traditional way, but we know that it needs to be less than that, so it's going to be below. Okay. Now let's go ahead, and my next one will be in blue. Let's do the 50% line. So that's y is greater than or equal to 110 minus 0.50x. Okay, we know that this graph is going to start at 110. So let's go ahead and find that. So this is 0. Here's 100. Here's 120. So reasonably 110 is exactly in between. Okay, and then we just have to pick another x value and plug it in. I don't see any reason for us not to use 100. Again, just because I know 100 is going to multiply by these decimals very well. So let's just go ahead and pick x as 100 again. Although you could pick any value you wanted. Okay, so let's just throw that in the calculator right there. 110 minus 0.50 times 100. and that is 60. So this is y is greater than or equal to 60. So 110, or 20, 40, 60 right here. Okay. And what I need to do is go ahead and connect these two dots. And then based on kind of what we talked about at the beginning, we know that this line is going to need to be above. Okay, so what we have here is we have our two lines, okay, and our 75% line and our 50% line. And really, what are we interested in? We're interested in this area in between, but not just the area in between, but the area in between the red and the blue line and the two black lines as well. How come also the two black lines? Well, we talked about that this is representing age 20 and this is representing age 70, and we're only interested in people between the ages 20 and 70. So we are interested in strictly this area, this quadrilateral in the middle. Okay, so this is my area I'm most interested in. So anything in here is somebody getting quality exercise. Their heart rate is high enough to get quality exercise in these ages. So let's just kind of break down the graph a little bit more to understand it a little bit more in depth. So like, for example, what is the target heart rates for a person at age 20? How can I figure this out? Well, I know that the target heart rate for age 20, I want to find age 20, and I want to go up here. Okay, so it looks like it's anywhere between the blue line and the black line. So just really anything right on this black line right in here. So to me, this looks like, let's just call this 150. And we can call this, oh, I don't know. My line's a little bit off. You know, we can call this approximately 100. Because it looks like, you know, if I really truly would have connected the dots, it might have actually gone through here. So it looks like I can say that definitively a person, it looks like between, looks like between 100 and 150 beats per minute. Okay, so let's just keep looking. Let's just keep trying to understand this. So like, if a person is 30 years old, as I'm about to be this fall, and that person is getting 85, their heart rate is up to 85, are they getting quality exercise? So let's find 30. And here's 80, and here's 85 is going to be probably right in here. Is that person getting quality exercise? No, they're not really raising their heart rate enough. They may just not be running hard enough or working hard enough or keeping their reps up in a good amount of time. Whatever the reason may be, no, they aren't, okay? Again, we're looking for, if I'm talking about a person age 30, we're looking for blue line to red line at age 30. So, again, anything in here would be a solution set. It is part of the algebraic solutions, but you know, you can look at the age and identify the range of their heart rate and whether they're getting quality exercise or not. All right. Although that this video was separate from the rest of it, just a little technical error on my half. Either way, that is the end of the lesson. Go ahead and just move on to the homework, and otherwise I'll see you next time for 2.4.